Good morning. This is a presentation involving much ado about offset vectors. In particular, it's about a kind of garbage collection algorithm which we've identified and named offset vector compaction. An offset vector compactor performs in-place compaction, and I'll first describe in-place compaction in order to explain why offset vector compactors are important. In-place compaction consists of three tasks, which occur after the collector has marked all the live objects. The compactor must compute a new address, called the forwarding address, for each live object. Ideally, it will do so in a way where all the objects will be pushed to one side of the heap, producing the most compact result. Then, the compactor updates all the references in the objects to refer to their forwarding addresses, and then the compactor relocates the objects to be stored in these new addresses. Unlike copying algorithms such as semispace, we don't need additional memory to perform in-place compaction, and unlike non-moving collectors, we still actively are defragmenting and compacting memory. Thus, collectors which use in-place compaction can be some of the most space-efficient collectors. But this abstract description glosses over that we need to somehow be able to map the objects to their forwarding addresses. And the way that we implement this mapping distinguishes many compaction algorithms from each other. The Lisp2 algorithm, one of the first compaction algorithms, implements this mapping by forwarding addresses by reserving a word before each object to store an address in. We assign increasing addresses to each live object, putting each immediately after the last object, plus space for the forwarding address. We update each reference to an object by reading the word before each referent object. We can finally then relocate all of the objects to complete the compaction. This algorithm works, but it has two main disadvantages. We first need to reserve space for each forwarding address. Now, in my example, I said there was a word to store each whole pointer. Some collectors are able to compress the address into the header by making them less than one word. But in any case, regardless of what size we end up with, we still need to have this spare space per object to store the forwarding addresses. We also can't reorder or fuse any of the passes together. In particular, we can't both update references and relocate the objects in the same pass, because we need the object and its forwarding address to be in the original location in order to retrieve the forwarding address given a reference pointing to the old address. So, could we somehow compute forwarding addresses on the fly without storing the addresses anywhere? Recall that we relocate each live object to immediately after, where we'll relocate the preceding live object too. Another way of stating this property is that we sum how much live data precedes an object in order to compute its forwarding address. This implies that we could just as well do a linear scan whilst forwarding an object, summing from the start of the heap to get to the start of the object. This algorithm would be heinously time efficient, but at the very least it doesn't require any space like Lisp2 does. This brings us to offset vector compaction. We can make this algorithm time efficient with little space overhead, not quite no space overhead, but nonetheless, we can introduce the eponymous offset vector, which captures parts of the sums that we were computing in order to reduce the amount of scanning which we need to forward objects. Suppose that we arrange for the tracing pass to set the mark bits for every live word in every live object, rather than just the first word of each live object. The mark bit map will then have marks for all the words which are live, and we're going to use this to compute the addresses later. The first pass of compaction is to compute a running total of the live data, storing the total every so many words into the offset vector. and for the sake of brevity, we're going to call that every so many words a block. Then, to forward a reference to an object, we read off the entry in the offset vector for the block which contains the start of the object, and we add the live values, scanning from the start of the block to the start of the object. The sum of just those two values is the sum of all the live data which precedes the object, but computed in a different order. Storing running totals in the offset vector thus bounds each scan to just one block, and the scan amounts to taking a population count, which is a fast operation on contemporary processors. Another trick with offset vector compaction is that we only use side tables to compute a forwarding address, so we can update the references and relocate objects in the same pass, because we never update or invalidate these side tables when moving objects. This eliminates one pass from the Lisp2 algorithm, and also eliminates one frame which I would have to draw and animate. We make 6 contributions with our paper. Broadly, we introduce the taxonomy of offset vector compaction algorithms and review their history. We implement a variety of offset vector compactors, including the one-pass compactor presented at ISMM'24 by Corey and Patton. We also introduce a new algorithm for computing the forwarding addresses based on a particular style of markup bitmap. And we finally evaluate all of these compactors on a modern OpenJDK with a Da Capo benchmark suite. I've already given my introduction to offset vector compaction, so I'm going to talk about the history and design space of offset vector compactors, and then our results from evaluating a bunch of compactor designs. Now, the simple offset vector compactor I described before is almost exactly that used in OpenMCL, which was originally known as Macintosh Common Lisp in the 80s, renamed several times, and now it's known as Clojure Common Lisp, Clojure spelled with a Z. The first open source release of OpenMCL had this collector algorithm in 2001, but there are references to the algorithm having existed since 1996. Now, my simplification only actually left out that they extended the collector to be generational, which fits rather naturally with offset vector compaction. Offset vector compaction preserves the order of the live objects, so all of the old objects will accumulate near at the start of the heap, and the new objects will be allocated near the end of the heap. We couldn't find any mention of this collector in the literature, which is surprising as this collector is the first instance of offset vector compaction which we've found. The first 3 instances we found of offset vector compaction are the OpenMCL collector, the parallel old-GC introduced in the SunJDK5, and the parallel mark compact collector by IBM described in the paper named An Efficient Parallel Heap Compaction Algorithm by Aboudiad et al. The compressor by Corey and Patton builds upon the IBM collector, introducing the use of virtual memory remapping for parallel compaction, and using page protection for concurrent and incremental compaction. The Android Runtime then introduced a concurrent mark compact collector, based on the design of the compressor, using the useFaultFD mechanism in Linux to handle page faults more efficiently than by using signal handlers and SIGSEG-V. Finally, the one-pass compactor, described in an intellectual abstract by Corey and Patton, extends the compaction algorithm of the compressor, with pointer threading-based compaction, to indeed perform all the steps of compaction in one pass. Now, I have some apologia for why we've invented another name for another set of algorithms. In my opinion, it's quite easy to look at this algorithm if you know the compressor and say, this is basically the compressor. But this neglects that the compressor wasn't the first offset vector compactor. If we're going by popularity, the SunGC and the Android GC are also by far the most widely deployed instances of offset vector compaction. Furthermore, the idea of offset vector compaction is independent of using virtual memory mapping for parallel and concurrency. None of the other collectors we found are even both concurrent and parallel. There are good reasons for this, but still. The Android Runtime, for example, does use a similar mechanism to the compressor for concurrent but not for parallel collection. It's more efficient on mobile devices to use a single-threaded GC, so there's no need to support parallel collection. The one-pass paper also suggests that you could use the mechanism with a one-pass compactor for parallel collection. But many collectors don't use that mechanism while still performing offset vector compaction. Some of the collectors fuse and also rearrange the compaction passes, further showing the breadth of the design space for offset vector compaction. We implemented various offset vector compactors in the memory management toolkit, including both the serial and parallel variants of the one-pass compactor. There are different parallel and serial variants, as the parallel variant introduces some synchronization needed in order to perform pointer threading with multiple threads, which we don't have in the serial version. We evaluate these collectors against the semi-space and IMIX collectors, which are the best performing canonical collectors in MMTK. And we evaluate them all on OpenJDK21 and the DaCapo-Chopin benchmark suite. All of the evaluated collectors are stop-the-world and full-heap collectors, and all but serial one-pass are parallel. The parallel offset vector compactors partition the heap into regions of 256 kibibytes each for parallelization. Now, you'll notice that there are three, flavors of the offset vector compactors, indicated by the suffixes with a hyphen or lack of on each name, and these all handle the mark bitmap differently. The names without suffixes use a style of mark bitmap similar to the compressor, and unlike the example I gave before. They mark only the first and the last bits of each object. The names ending in CL-mol do the same, but they use a branch-free algorithm based on carryless multiplication, which we describe in the paper. The CCL suffix names mark all of the bits of the object, as Clojure Common Lisp does. All of the evaluation that we do is performed on a 16-core, 32-thread Zen 4 processor. We first evaluate our offset vector compactors against the canonical collectors in a parallel setting. All of the variants of offset vector compaction perform fairly similarly to these canonical collectors, but the branch-free variants have a clear performance advantage over the branchy variant. Both CCL and CL-mol variants approach, but are still outperformed by IMIX. But the vanilla OVC is closer to semi-space. Nonetheless, all of the offset vector compactors can run the tightest heaps of all the evaluated collectors. The two branch-free variants perform fairly similarly, but the CCL variant does slightly and consistently outperform the CL-mol variant. It's surprisingly slightly more efficient to set all the bits for all the live objects while marking with the CCL algorithm, rather than just the first and the last as we do with CL-mol. We assume that this is because the branch-free algorithm which we introduce in the paper for passing the mark bitmap in this style is slightly more complicated than just taking the population count as CCL can. Setting all of the bits is actually faster than it might sound, because you can set bits, whole words at a time, and all the objects tend to be quite small, so you're not actually setting that many bits at a time anyway. We then evaluate the parallel one-pass against the parallel offset vector compaction. Surprisingly, one-pass seems to lag offset vector compaction by a decent margin. So we looked and investigated what the causes could possibly be for the slowdown. We did so by using our serial version of one-pass, which, if you recall, does not have this region-based design, and it also avoids all the synchronization needed for parallel pointer threading. We found that the serial one-pass performs much closer to offset vector compaction on a single thread. But the parallel one-pass, even though that's still running on a single thread, does consistently lag both. We then did a scalability analysis, which is better described in the paper, and found that the scalability of one pass and the offset vector compactor is similar for all the thread counts in between 1 and 32 threads. This suggests that, as Corey and Petrank had suggested, the contention between threads is very low, but the synchronization mechanisms themselves are introducing a fair bit of overhead. We also measured how often either version of one pass resorts to using pointer threading. The parallel version, which uses the heap partitioned into regions, also performs more threading than the serial version, which doesn't. Likely due to these regions producing a different placement of objects in memory. Corey and Petrank suggest several suggested strategies for parallelizing the one-pass compactor, and it is possible that we picked an ill-suited strategy. In fact, the strategy we chose isn't in the one-pass compactor paper, but we thought it was a decently canonical one to have, so that's why we implemented it. Still, we think that implementers of one-pass will have to consider how parallel collection algorithms may partition a heap, and how the partitioning will affect the placement of objects in order to obtain the best performance from their collectors. Another issue to consider is that one might think going from 2 passes to 1 pass is a larger reduction in work than it actually is. At face value, halving the number of passes might suggest the collector somehow performs half the work, by some sense and measure. We ended up changing our informal language in the lab to compensate. We would say that the compressor really has 1.5 passes, which in some sense is a very strange thing to say, because a pass is a pass, and you can't only say it's a half. But the pass which computes the offset vector only has to traverse the side tables, the mark bitmap on the offset vector. And these have a combined memory footprint of only a few % of the size of the actual heap, and so they are less demanding on memory bandwidth. The other pass of the compressor, and some other passes of similar collectors, does traverse the actual heap, and also has to pass objects to update their fields and do more complicated acts. And subsequently, those passes tend to be an order of magnitude slower than computing the offset vector. This is all to say that offset vector compactors are a worthwhile subject to investigate. The lights in this room might disagree with me. I do think they are a worthwhile subject to investigate. Offset vector compactors are everywhere. Many Android phones, to this day, and Java users, admittedly up to JDK 23, but that's still pretty recent, they all use offset vector compaction. We found that offset vector compactors are competitive with the canonical algorithms, outperforming semispace and slightly lagging IMIX in our evaluation with MMTK on OpenJDK and Dacapo. We also found the one-pass compactor offers an algorithmic improvement over 2-pass offset vector compaction, but the additional synchronization in a parallel setting does still undo the speedup provided by one-pass, even when contention is not an issue. So, thank you very much for your time. Steve will now take questions, as he is much more conveniently positioned on the other side of this screen. Goodbye.
So Steve's going to take questions. Questions?
So if I remember correctly, IMIX does reference counting as part of its internal. IMIX does reference counting as part of the main GC algorithm. No,
you can compose IMIX and reference counting. IMIX is just like the base algorithm, the canonical base algorithm.
My question
so it's
is
just a tracing algorithm. Yeah.
So you showed the absolute numbers. I'm wondering if the metric that you should compare is like the number of relocated objects. Like
the number of
relocated objects. Because they might vary depending on the algorithm a lot.
Oh, absolutely. Yeah, so semi-space will relocate every object. We didn't have here a good high-performance mark sweep algorithm. If we did, that's another canonical algorithm, which we would have liked to have included here, but we didn't have a good enough performing one to put in the evaluation, and that would move exactly no objects. Semi-space and mark compact move all objects, and IMIX moves some objects. So yeah, they're distinctly different algorithms. The reason why we put them on the screen is because these are ones that people use as basis to make richer, more interesting algorithms. So hence their canonical base algorithms. So I think most algorithms today are some composition of mark sweep, mark compact, semi-space, or IMIX. Most production collectors today use some combination of those, plus parallelism, concurrency, and and that composition. But yeah, they'd move very, very, very different numbers of objects, and there's an obvious trade-off to be made there.
Cool. Any more questions?
Yep.
So in the evaluation, I saw a lot of, for example, mentions to like using this on Android in part because of concurrency concerns. Is this approach also applicable on a server architecture with cores? Is there a reason it's better or worse than any other technique? What is the situation on?
It very much depends on the context. So mark compact is used by the old Sun or OpenJDK parallel collector in the old space, and it was originally an offset vector compactor. So it's very, very heavily used in serving computing and in Android. The comment that Hayley made in the talk was that in Android, it's not parallelized, which is the difference with Compressor. Compressor is concurrent and parallelized, but in Android, they're not parallelized, and the reason there is the deployment platform on a phone doesn't make parallelization of the GC profitable.
I have a quick.
Yep.
So on .NET, I know that it doesn't actually, so it does do that kind of compaction, but it uses the gaps between objects, so it moves blocks, or I think it calls it plugs. So a range of objects, and there's always a gap either side, and it keeps track of the offsets in this free space. So it's worked out which areas aren't accessible, and then it uses that somehow. I don't know if that's at all interesting.
It is interesting, and Hayley did look at that, but I think it was a little bit hard. It's not very well documented, the algorithm. I mean, that's not a criticism, it's just not a published paper on it. So it was a little bit hard for Hayley to really pin down exactly what the algorithm was. We would have liked to have done. And one of the, I think for me as someone who's been in the field for a really long time, I think one of the really interesting things that Hayley did was discover these old implementations dating back actually probably before 2000 that did offset vector calculation. I, in my head, just thought of Compressor as being the first implementation, but it's by no means the first. Yeah, yeah, we would love to have had that in the thing, but we just didn't have the information.
Cool. Okay, I think we need to move on to the next one.